The object will come closest to Jupiter on March 16th, 2026, and it will arrive exactly at the right distance to Jupiter, to within a small fraction of a percent, exactly the right distance, where the gravity of the sun will not be able to tear apart any probe that it releases near Jupiter. So it arrives just at the right distance so that Jupiter's gravity will overcome the sun's tidal gravity, and anything it releases there will stay there, which suggests, why did it arrive exactly at that distance? In order perhaps to release some probes near that planet. So there are lots of questions. It also shed nickel with very little iron, lots of anomalies, and NASA did not discuss them. Instead of what they did, which is to say, we pretty much know that it's an object of the type that we have seen before. They should have emphasized the mysteries, or they should not have held a press conference because they didn't have much new information there.
3I Atlas has astonished astronomers yet again, with twin jets that stretch into straight, unwavering plumes across millions of kilometers. In fact, many argue should be impossible under established comet physics. In the past several weeks, this object passing through our solar system has displayed behaviors that even seasoned researchers struggle to explain. According to Harvard astrophysicist Avi Loeb, these anomalies may indicate that 3I Atlas is far more unusual and potentially more concerning than first assumed, suggesting that standard natural explanations are becoming increasingly difficult to defend. The stark clarity of 3I Atlas's twin jets lies at the center of the mystery. Cometary jets, driven by sunlight warming pockets of ice, erupt in irregular, shifting fountains. As the nucleus rotates, the streams should arc, bend, and fan outward, creating diffuse structures that broaden over time. Yet 3I Atlas defies this logic. Instead of blossoming outward in chaotic plumes, its jets form straight, pencil-thin beams that hold their shape over extraordinary distances. Long exposure images taken on 9 November 2025 show the jets extending outward for more than 1 million kilometers without any sign of wobble or deformation. They appear fixed in space, rigid as rails, seemingly independent of the comet's measured 16.16-hour rotation period. Early in the observation campaign, some researchers hoped the strange geometry was an illusion, perhaps a coincidental alignment or a quirk of imaging. But repeated measurements from multiple platforms quickly dispelled that possibility. Hubble's ultraviolet imaging confirmed the jet's stability. SPHREX recorded the same narrow plume angles. JWST captured thermal maps revealing the jets as heat signatures extending beyond the visible structures. Even the Mars Reconnaissance Orbiter, observing from a completely different vantage point, documented the same unblinking geometry. The more data scientists gathered, the harder the anomaly became to dismiss. Thermal imaging added another layer of complexity. The nucleus of 3I Atlas is encircled by concentric heat rings with surprising symmetry, accompanied by a noticeable suppression band that interrupts the expected thermal gradient. Analysts have referred to these features as extraordinary anomalies, a label that has made its way into technical papers with rare unanimity. The pattern suggests that heat is being distributed in a structured way across the nucleus, something that does not align with simple solar heating of an irregular, porous body. That structure has prompted speculation about layered composition, complex internal fractures, or something even more exotic. But while the morphology remains deeply puzzling, the composition of 3I Atlas appears conspicuously ordinary. Spectroscopic analysis from the James Webb Space Telescope, covering wavelengths from approximately 2 to 12 microns, indicates that the coma is dominated by carbon dioxide. Quantitatively, CO2 emission lines constitute the majority of detected volatile flux, with water vapor and carbon monoxide appearing as secondary components. The presence of amorphous water ice, crystalline water ice, micron-sized dust grains, and fine particulates is fully consistent with the inventories of volatile-rich comets originating in cold, distant regions of planetary systems. These materials and carbonaceous dust are typical signatures of nuclei formed under low-temperature conditions beyond the ice lines of their parent stars. The CO2-H2O ratio is notably high, but not without precedent. A small subset of solar system comets, such as C-2016-R2 pan-stars, have exhibited similarly elevated CO or CO2 abundances relative to water, although values above 5:1 remain rare. Such ratios suggest either an intrinsically CO2-rich formation environment or strong thermal processing that depleted water ice while preserving or mobilizing CO2. JWST's spectral modeling shows that the detected CO2 is not a calibration artifact and maintains consistent line strengths across repeated observations, reinforcing the reliability of the ratio. Near-infrared observations from ground-based telescopes and space instruments further identify abundant water ice grains in the coma, including submicron and micron-scale particles that scatter light with a profile similar to dust observed around D-type asteroids. These asteroid types, commonly found in the outer main belt and among Jupiter Trojans, are characterized by dark, carbon-rich surfaces with low albedo. The spectral slope of 3I Atlas's dust, showing a neutral to slightly red reflectance, is broadly consistent with that category. This suggests the nucleus contains primitive materials similar to those found in carbonaceous asteroids or Kuiper Belt objects, substances considered some of the most ancient and unprocessed in planetary systems. Crucially, spectral data reveal no exotic elements, no high-temperature alloys, no engineered composites, and no anomalous isotopic ratios that would fall outside known astrophysical production pathways. The hydrogen and oxygen isotopic profiles within water vapor fall within ranges observed in long-period comets, and carbon isotopes in CO2 and CO show expected cosmic distributions. Silicon, magnesium, and iron signatures correspond to common silicate dust compositions. JWST, Hubble, and SphereX datasets show no narrowband features associated with industrial compounds or artificial polymers. In short, nothing in the composition suggests an artificial origin. The materials are exactly what would be expected of a natural, volatile-rich interstellar comet. This juxtaposition, an entirely conventional chemical makeup paired with morphological behavior that diverges sharply from standard comet physics, forms the central tension surrounding 3I Atlas. NASA has maintained a conservative position, categorizing the object as a natural comet with unusual activity. Official statements emphasize that cometary jets can behave irregularly and that interstellar objects may present behaviors unfamiliar to scientists accustomed to solar system examples. However, internal discussions reported among researchers acknowledge a significant unresolved issue. No conventional model of sublimation-driven jets can maintain narrow, straight, highly collimated plumes over distances exceeding 1 million kilometers without substantial deformation. Under known physics, cometary jets broaden as particles move away from the nucleus due to thermal expansion, radiation pressure, rotation-induced smearing, and solar wind interactions. Jets also curve, fragment, or fan out as the nucleus rotates, especially over multi-hour periods. Yet 3I Atlas demonstrates jets that remain geometrically stable with minimal angular dispersion, despite a measured nucleus rotation period of approximately 16.16 hours. Observations from JWST, Hubble, HiRISE, and multiple ground observatories show no evidence of rotational modulation in the jet orientation. This absence of rotational smearing remains one of the most challenging features to reconcile with known cometary outgassing dynamics. Avi Loeb has publicly emphasized this contradiction. He notes that although unusual comets exist, comets with asymmetric jets, volatile anomalies, or unexpected rotational states, none exhibit the degree of precision observed here. Natural outgassing produces turbulence, irregular flow patterns, and stochastic bursts, not long-lived linear structures. In Loeb's assessment, extremely stable jet alignment over such vast distances implies a regulating mechanism. If the jets were powered solely by solar-driven sublimation, the mass loss rate required to sustain such coherent plumes would likely impose structural stresses exceeding the tensile strength of typical cometary nuclei. In that scenario, the object should show signs of cracking, fragmentation, or rotational acceleration due to uneven momentum loss. Instead, 3I Atlas shows no detectable fragmentation, maintains structural integrity, and exhibits no anomalous spin-up, conditions inconsistent with the jet power inferred from imaging. For Loeb, this leads to an uncomfortable but logically derived possibility. The jets may not be natural vents, but regulated emissions that behave more like directed exhaust. He acknowledges that this interpretation is speculative and requires evidence beyond morphology alone. Nevertheless, he argues that the extreme collimation and stability observed so far push natural explanations to their limits. Without invoking an internal mechanism capable of maintaining directionality, whether natural or engineered, the behavior remains physically anomalous under existing comet models. Whether the emerging data will eventually support a natural explanation or require a fundamentally new interpretation remains unresolved. But the compositional normalcy contrasted with morphological precision continues to drive one of the most significant scientific debates regarding an interstellar object to date. The thought is provocative, but the rest of the scientific community remains cautious. Many argue that with only 3 known interstellar visitors, our understanding of such objects is far too limited. Interstellar comets may evolve in pressure environments, thermal histories, or gravitational fields entirely different from our own. They could carry exotic volatile layers or internal cavities that produce jet patterns unknown to solar system models. The deep negative polarization branch observed in pre-perihelion data, unprecedented in any known comet, supports the idea that its dust grains may possess unusual geometries or surface structures. These traits, though odd, do not require an artificial mechanism. Still, the straightness of the jets remains the stumbling block. Solar wind should distort them. Radiation pressure should bend them. Particle interactions should broaden them as they travel outward. Yet none of these effects appear to occur. Instead, the jets maintain coherence far beyond any scale that natural plume physics can justify. Even modeling attempts using extreme assumptions, such as superpressurized vents or temperature-regulated chambers, fail to replicate the observed structure. Something is stabilizing those jets, and at present, no consensus model exists to explain what that something is.